So folks, I'd like to make a quick video about this problem here. It's sort of a nifty problem, a little bit different than what we've seen before. Because here I'm given a graph of something, but I'm told in the problem statement that this is not the graph of a function f, it's the graph of the function f's derivative. Okay? So although this is my x-axis here, the graph is of f prime of x. And so we're going to have to sort of work backwards here, and it's a really good exercise for this problem. Before we do any of these questions, what I'd like to do is I'd like to make a pair of charts that you're going to use through the rest of this unit. So the first chart that I want to say it like this, and I'm going to be careful with my implication arrows, but I would say that when you're memorizing this, don't really worry about those arrows. Instead, just know that at the end of the problem, you have to apply a little bit of common sense. So let me say this. If f prime is greater than 0, if the function's greater than 0, we know that that implies that the original function is increasing. Okay. If f prime is less than 0, then that implies that f is decreasing. So that arrow there, that just means implies. And I don't want you to worry about that too much right now. What I want you to do is kind of keep track of, if I want to know about where the function's increasing, I'm going to look to see where f prime's positive. And likewise, if I want to know where f is decreasing, I'll look to see where f prime's negative. But then I'll just have to be a little bit careful when I give my answer. The second chart is a little bit longer than that. And what I want to say about this is that if f double prime is positive, then what do we know? Well, just like this chart said, if a function's derivative is positive, then the function's increasing, but we're sort of stepped down a level here. So if f double prime is positive, that implies that the original function, or excuse me, that its parent function, which is the derivative, is increasing. But that's precisely our definition. So I'm putting the if and only if arrow because that's our definition. You don't need to worry about that. But when the derivative is increasing, that's exactly what we mean when we say that f is concave up. Likewise, if f double prime is less than 0, that implies that f prime is decreasing, which is our definition of, let's see here. Here I'm saying the slopes of the tangent lines are becoming more negative. The slopes of the tangent lines are becoming more negative. That's precisely our definition for f being concave down. And so here's that second chart. So what I highly recommend you do is you put both these charts on flashcards and spend some time studying them. Real quick, folks, I was careful with these arrows here. And let me just show you what I mean. If I have this function right here, say our regular old cubic function, the function x cubed, let's just look at that here. So there's the function x cubed. Notice that x cubed has a horizontal tangent line right here. And so what's the sign on the derivative? F prime of 0 is equal to 0 because of that horizontal tangent line right there. But if I were to ask where is the cubic function increasing, f is increasing on the entire interval from minus infinity to infinity. So even though the derivative was 0 there, that doesn't mean that we don't include 0 in this particular case, because we were increasing before we got to 0, we were increasing after we left 0, and 0 is where the function's defined. So I do get to include 0 on that particular interval. Just to show you where you do have to be careful, folks, though, if you were to encounter some more complicated function, like this one right here, and if I were to ask you where is f increasing, here you would have to say that f is increasing on minus infinity to 0, and then again from 0 to infinity, and I couldn't put those two intervals together. So that's why I'm saying why you have to sort of use some common sense when you're applying this. Certainly if the derivative exists and it's positive, then it's possible to draw some interval around that place where the derivative is positive and say that we're increasing on that interval. And that's what this first chart is telling you. So folks, that's why I'm being careful with those arrows there, in some cases just using the implies, in some cases using the if and only if. I would just say that you don't really need to worry about the arrows, but you do need to apply some common sense when you're trying to use these two charts. Okay, so now we're ready to go ahead and tackle these questions. I'd like to actually do them slightly out of order. Let's do letter B first. Letter B asks the question, on which intervals is the function decreasing? Okay. Now, Careful, folks. It would be incorrect, so please don't write this down. It would be incorrect to say this is where the function is decreasing. Why? That's assuming that I'm looking at the graph of f. I'm not looking at the graph of f here. I'm looking at the graph of f prime. So instead, since I'm looking at the graph of f prime, I want to know where the original function is decreasing. Well, I can use this second line of the first chart right here, this second line right here, to help me decide that if the derivative is negative, I know for sure the function's decreasing on that interval. Notice the derivative starts taking on negative values just to the right of 3, and so this function is decreasing from 3 to infinity. Now careful here. The function, the original function, f of x, which I'm not sketching the graph of. I don't know what the graph looks like, although I could try to build it if I wanted to. But I can still answer the question that the original function f is decreasing from 3 to infinity. And I know that because f's derivative, which I have sketched here, has negative y values. Again, I'm not talking about the slopes of the tangent lines of f prime. I'm talking about the y values on y prime. This point right here, for instance, this point right here, for instance, has a negative y value. This point right here, for instance, all right, we're going to play games, has a negative y value. And all of the places where the derivative of the function has negative y values, that's precisely where the original function is decreasing. Okay, let's keep going. So on which intervals is the function increasing? Okay. Well, you'd be kind of correct if you first thought you would write the answer this way. So hold on, don't write this down just yet. If you wrote from minus infinity to 0, and again from 0 to 3, you would be correct if that's what you put as far as you are increasing on this interval, you are increasing on this interval. But because I was increasing before I got to 0, and since I was increasing after I left 0, I get to include 0 in that interval. So that's actually not correct, and the answer is from minus infinity to 3. Okay? The issue is that for this particular function, although I don't know what it looks like, I haven't sketched the particular function, I've got something like this happening here, where I'm increasing till I get to 0, and I'm increasing for a little while after I leave 0. My derivative is 0 at x equals 0, but I'm increasing over any interval that includes 0. So the function is decreasing on the interval from 3 to infinity. Okay, let's go ahead, and since we're looking at the graph of f prime, let's state where the original function, and by the way, I should have been a little more careful here. I'll fix this in your question. Give the location of any extrema of f. So let me just add right here, of f, and be sure to label it as a maximum or a minimum. Let's see here. Notice that at x equals 3, f prime changes from positive to negative. But that tells me that the original function, f, changes from increasing to decreasing. So that tells me, so x equals 3 is a local maximum of f. Notice that this function has one other critical number. I didn't ask you to state the critical numbers, but the original function, let's just say this, f has critical numbers at x equals 0 and at x equals 3, because those are the two places where f's derivative, which I have sketched here, takes on the value 0. Okay? So notice that one of these critical numbers, in fact, did not give us a local max or a local min, and the second one at x equals 3 gave us a local max. Okay, so we're almost done with this problem. We're ready to keep going here. On which intervals is f concave up? Well, that's a question. Where is f concave up? Well, f is concave up where f prime is increasing. So to answer the question, where is f concave up, I'm simply going to ask, where is the original function increasing? And the original function is increasing from 0 to 2. So this function here, f prime, it is increasing from 0 to 2, so that's precisely where f is concave up. Now, on which intervals is f concave down? It's concave down, so let's just say that. F is concave down. F is concave down where f prime is decreasing. And f prime is decreasing on the interval from minus infinity to 0, and again from 2 to infinity. The graph that I'm looking at, f prime, is decreasing on this interval and on this interval, so that tells me the original function must be concave down there. Okay, finally folks, let's give the location of any inflection points. Well, notice that at x equals 0 and at x equals 2, the graph changes concavity. So x equals 0 and x equals 2. Now careful folks, I'm not talking about inflection points of f prime, right? I'm looking at the graph of f prime. If I had asked you for an inflection point f prime, the answer is maybe somewhere around here, maybe at 1 or something like that. I'm not exactly sure. But I'm not asking you where f prime has inflection points. I'm asking you where the original function has inflection points. The original function has inflection points where f prime changes from increasing to decreasing or from decreasing to increasing, i.e. at the max and mins, so at the local max and mins of f prime. And that finishes up this question. Folks, this is a really tough concept. We're having to work backwards here, right? We're looking at the graph not of f, but of f prime. It's tough to work backwards with these problems. Rework through this problem a second time. Convince yourself that this all makes sense, and we will work through these in our class session coming up. Thanks for your patience, folks. Let me know if you have any questions.